So this is our lecture on molecular polarity, and this is going to stem directly from a lecture that we finished last Monday on molecular shapes. So polarity is an extension of what we covered previously in chapter 3. We looked at ionic bonds, in which one atom gives away an electron, and then you have a charge between two atoms. So say, for instance, just as kind of a reminder, ionic compounds have ionic bonds, and that's where the sodium atom gave away its electron to the chlorine atom. In that process, sodium became a cation, chlorine became an anion, and now they're attracted to one another by virtue of that separation of charge. And this is a true ionic bond because it's between two ions. And over here we talked about covalent bonds in this chapter, where we have two atoms which are sharing electrons. Like, let's look at H2. We've got two electrons here. One hydrogen brings one electron to the table. Another hydrogen brings another electron to the table. And they share those two electrons, and that makes a bond. And I'll describe the ionic bond like a high school relationship because it's just based on attraction only between the two, the positive and the negative. And the covalent bond, I like to describe kind of like a marriage relationship because there are assets involved, that these two electrons are shared. And if these two hydrogens want to split up, well, they have to hire a lawyer and determine who gets the electrons because both of them want the electrons, and it's going to be a big mess. So that's kind of what we've been talking about. But what we're going to talk about today is that there's actually a spectrum here between purely covalent and purely ionic bonds. And in the middle, we can have these bonds which we call polar bonds. They're still covalent, they're still sharing, they just don't share them equally. Polar covalent bonds. And this occurs where you have two atoms that are different in specific ways, attached to one another, like say H and Cl. It's still covalent bonds, so we're still just going to see these with nonmetals that are involved in covalent bonding. But they don't share the electrons equally. We find that some atoms are electron hogs. They're kind of bullies on the playground. And so we've got this hydrogen came in with one electron. This chlorine came in with 7 electrons, and he's sharing one of the 7. But chlorine's a little bit of a hog. And so even though they're sharing these 2 electrons, they're spending a little bit more time at chlorine's house. And hydrogen's just hanging out hoping that he gets, his share of these 2 electrons here. Because electrons have a charge, then we find that since chlorine is taking a little bit more of that electron density, it gains a little bit of a partial negative charge. This is a lowercase Greek d, which is a delta, which stands in this case for partial. So partial negative charge because it has a little extra electron density, and electrons have a negative charge. And in contrast, hydrogen here has a partial positive charge because it has lost some of that electron density. It's lost some of that negative charge here. So complete charges, +1, -1 on the ionic side. No charges on the perfectly covalent side. And somewhere in the middle, we have this polar covalent region where we end up with a partial positive and a partial negative. And maybe this is like a partial, like a +1/2 of a charge and a -1/2 of a charge. Maybe it's just a +1/4 of a charge. We're not going to get into that kind of a detail. We're just going to say that at some point, some of these are going to have a little bit of a charge. So the question is, how do we know? And what we're going to do is look at something called table of electronegativity values. So electronegativity is this measure of how much of a bully, how much of an electron hog these atoms are. So here's something you need to understand, electronegativity. This is a measure of how much an atom will attract electrons in a shared bond. And an atom which attracts electrons more strongly then is going to be a little bit more of an electron hog. Now, you can find the table of electronegativity values in your book. If you have the old edition, it's on page 129. If you have the new edition, I'm not sure exactly what page it's on, but one of you guys can find it and post that. Here's one of my lecture notes. I will give this to you on the exam. You do not have to memorize electronegativity values. Thank you, Meg. Meg says it's on page 120, so it's pretty close. You do not have to memorize these. Never will you ever have to memorize these. Okay. I'll give it to you on the test, so you'll have it there. And really, it's just a matter, the higher the electronegativity value, the stronger the electron pull is. So fluorine here is the highest electronegativity, 4. Rubidium here for this particular table has got the lowest. So you see that it increases as we go this direction, essentially. Yeah, there's no reason to make you memorize this. And what we're going to do to determine if a bond is polar is just compare the two numbers. So in the example that I gave you previously, we looked at hydrogen bonded with chlorine. You see that hydrogen has a value of 2.1, chlorine has a value of 3.0. That's a difference that's big enough we can say that's a polar bond. And we'll show you what those differences are in a minute, but first I want to direct you over to your in-class activity sheet, not chapter 5, number 2, or chapter 4, number 2, whichever one you want to call it. And part 1 is just assign electronegativity values to the elements. It's literally like look it up on the table and put it down on the paper. I think you guys can do this section. Help me out here. Nitrogen is what, if you've got your book open? 3.04 or 3.0. We're not even going to worry about more than 2 digits. Excellent. What about iodine? Iodine? 2.5. Okay. I don't have all these memorized, but I've got a good idea for most of them. Sulfur? 2.5. Phosphorus? 2.1. Hydrogen? 2.1. Okay. I think you guys get the idea. You guys can manage this, right? At least 4 of you guys are with me here. Okay. All right. So let's go back to how we know whether a bond is polar or not. And here's what you do need to memorize. Okay. It's just this little line chart. Right? Let's see. Right here. The barrier between completely covalent and polar covalent is going to be about 0.5. The barrier between polar covalent and ionic, we're going to put it about 1.9. Or if you prefer, if we were just looking at this chart up here, it's backwards from how I did it, but it doesn't really matter. We're going to say this is about 1.9 and this is about 0.5. You guys following me here? These numbers are the differences in electronegativity values between the two things that are bonding. So if H was 2.1 and chlorine was 3.0, we take the bigger, we subtract the smaller, and we find that the difference here is 0.9, and that's definitely in between 0.5 and 1.9. So we know that it's polar. And then once we know it's polar, the next thing we can say is, all right, because the chlorine was the one that was bigger, this is a side that gets a partial minus charge because it's the one that's attracting extra electron density. And since the hydrogen's value was lower, this is the side that gets a partial positive charge because it's losing a little bit of electron density. Everybody with me here? Got it. Excellent. Okay. Now, before we continue, I want to emphasize to you guys that this is a spectrum. Okay. Previously, I told you the world was black or white. And now I'm telling you that the world is black and white and gray. All right. But what I really want you to see is a spectrum here, that if you're over here, you might be polar, but you're really, it's kind of a weak polarity. And if you're here as highly polar, at this point, you are mostly ionic, but, you know, getting close to being polar. At this point, you're mostly covalent, but getting close to being polar. It's a spectrum, right? It's not just black, white, and monochrome gray, but bonding is there's a larger spectrum than just these three classifications, okay? I want you to understand that. Even though we are in this, for the purposes of this class, going to say covalent, ionic, or polar. Sometimes we'll call this non-polar covalent as opposed to polar covalent, but it is a spectrum, okay? So if ever something lands on 0.5 and you're like, oh, I don't know, rather than saying, you know, which one is it? It has to be one or the other. I kind of want you to recognize that you could call it mostly non-polar, slightly polar, kind of either direction. All right, so let's look at our in-class activity sheet, and that's actually, oh, next one. This whole section, section 2, is doing exactly what we did there. And we've already done it for hydrogen and chlorine, so let's just do it here. So first, tell whether the bonds are polar or non-polar. And in order to do that, we're going to assign electronegativity values. Hydrogen's 2.1, chlorine is 3.0. So the difference here is 0.9. So then we're going to say, yes, it is polar. And then it says, show which side has accumulation of negative, which side has accumulation of positive. And this is where we're going to say partial negative on the chlorine, partial positive on the hydrogen. There is one other way we could show this. Sometimes people use these little vector arrows. It's an arrow with a plus tail, and the plus tail goes on the side that has the partial positive. And the head, the line, shows the direction the electrons are pulling towards. Either of those are appropriate. You could use whichever one you want. We don't need to use both. But let's do a few more just to make sure that we're all still on the same page before we move on. Let's try OH. You guys tell me, is that polar or non-polar? Shauna says polar. Why? Oh, Hogsett, that's exactly right. I'm not challenging you. I want to have you justify your answer so that everybody else can see how you got the answer polar. So, oh, Hogsett, why? How do you know? You're not wrong. You're totally right. I just want you to explain. Perfect. O is 3.5 and hydrogen's 2.1. Good. And therefore, the difference between the two is 1.4. Excellent. And 1.4 is the range. Here, we'll just copy and paste that little table, right? Nonpolar, polar, ionic, 0, 0.5, 1.9. So 1.4 is definitely in this range. So that's definitely polar. Excellent. And Shauna says oxygen hogs it. So therefore, my oxygen gets the partial negative and the hydrogen gets the partial positive. Perfect. All right. Let's do another one. Let's do carbon, oxygen. Is that polar or non-polar? Polar, excellent. And why? Because the difference is 1. Excellent. I think that's what Caleb meant when he said 1, because carbon is 3.0 and, no, sorry, pardon me. Carbon is 2.5 and oxygen is 2.5. Oxygen is 3.5. Is that what I said? Maybe Caleb should explain it. The difference is 1. That's right. And 1 falls between these two differences. And so this is polar. So which side gets the partial positive? The partial positive. Yeah, the positive is going to be the one that is lower. So the partial positive goes on the carbon, partial negative on the oxygen because it has a higher value. You guys with me here? I went from 4 people responding in section 1 to 2 people responding in section 2. So I just want to make sure that everybody's still with me. Excellent. Do you want to do a few more or do you feel comfortable with these? Few more, no problem. Diana says. What about nitrogen with nitrogen? Polar, non-polar? Shauna Meredith says non-polar. She's exactly right. And it's because nitrogen is 3.5 and the other nitrogen is 3.5. So the difference is 0. Basically, anytime you have 2 things bound together that are the same, the difference will be 0. So it will definitely be non-polar. Good. Let's do one more. Let's do carbon and fluorine. Polar, non-polar? Robin says polar. Shauna Meredith agrees. Okay, can you guys explain why? Justify your answer? I don't ever ask essay questions, but this is the type of essay question that I might ask. Is this a polar or non-polar molecular bond? And you tell me why. You will definitely have the electronegativity chart on the test. You will not have this little line graphic on the test. Excellent. Carbon is 2.5. Fluorine is 4.0. The difference is 1.5. That definitely falls in the polar range, so that's why it's polar. Excellent. So which side are the electrons being pulled towards? Which side gets the negative charge? The fluorine. Yes. So we could say partial positive on this side, partial negative on this side. That's if we wanted to use that little vector arrow. Or partial positive on the left, partial negative on the right. Okay, I think we're pretty good on these, so let's move on to the polarity of molecules. This is just looking at an individual bond, right? The bond between 1 carbon and 1 oxygen atom, bond between 1 carbon and 1 fluorine atom, and it's going to get a little bit more dodgy when we have to say, what about an entire molecule? Is a molecule polar or not? And before we say that, let's kind of want to emphasize, look again at what polarity is, right? If something is non-polar, there's no separation of charge. If something is polar, then you end up with a little bit of a separation of charge. And if something is ionic, you have a complete separation of charge. Everybody understands that, right? I hope. Anybody? You guys with me? Excellent. Okay. I've got 2 people with me. That might be enough. Okay, just to get started here. All right. I want you to also look at polarity as from another perspective. And that is that polar molecules have 2 poles, like magnetic poles, right? You have a north pole and a south pole, right? Here I have a plus pole and I have a minus pole. In order to be polar, I have to have 2 poles. There's no such thing as having like 1 pole. It wouldn't make any sense to have like a north pole but no south pole, right? It only makes sense when you have one in reference to the other. And so when we look at polarity of molecules, that's what we're going to be looking for. We're going to be looking for one side that has a plus pole and one side that has a minus pole, 2 poles. Okay, so in order to help us visualize whether something has 2 poles, I'm going to copy 2 molecules over here for you from the lecture notes. But first I'm going to, let's see, we're going to look at carbon dioxide and carbon monoxide. And before I continue, I also want to emphasize, this is very important, we can't look at molecular polarity unless we are looking at the molecules in their actual geometric shapes. So we're not going to be able to accurately predict molecular polarity unless we're already very good at determining and visualizing and drawing our VSEPR shapes. You guys with me here? I think we had this conversation on Wednesday. You have to be able to draw Lewis dot structures in order to properly determine VSEPR shapes. And you have to be able to properly determine VSEPR shapes in order to determine molecular polarity for reasons that we're going to see here in just a minute. Okay, so every step of the way here, very important. Okay, we determined in class activity sheet 5.2 that the carbon-oxygen bond is a polar one. So if we're looking at carbon dioxide, and I said something like, is carbon dioxide polar or is carbon monoxide polar? You can't just look at these 2 atoms and say, oh yeah, the molecule is polar because the bond is polar. Because I have to look at each bond individually, and I have to see how it relates to the shape. Okay, so here's my carbon dioxide, here's my carbon monoxide, and I know that the carbon-oxygen bond is polar. So this carbon-oxygen bond, this one right here, is polar. I could say I've got a partial positive on this carbon and a partial negative on that oxygen. Everybody agree with me here? I'm hoping. And I can do the same thing for this carbon-oxygen bond. This carbon-oxygen bond is polar. There's a partial positive on the carbon and a partial negative on the oxygen. Okay, and remember we came up with that because carbon was 2.5 and oxygen was 3.5. So the difference here was 1.0. That put it in the polar covalent range, so we knew that we had this separation of charge. Okay. Now, if I sit down and look at this molecule, not an individual bond, but the whole molecule, can I find one side of the molecule that's positive and one side of the molecule that's negative? I'm going to call this a line test. Is there a place where I could draw a line and put all my positives on one side and all of my positive negatives on the other side so that I'd have 2 poles, a positive pole and a negative pole? Jay Houston says, no, there's no place I can draw a line that's going to give me all my positives on one side, all the negatives on another side. I want at least 2 other people to look at this molecule and either agree with Jay Houston or disagree with him and tell me where to put this line. Okay, you guys all agree with him. There's nowhere to put this line. If I put the line here, nope, I've got one of each on either side. Okay, if I put the line here, I've got one negative here. So there's not one side that's polar that has a negative pole and one side with a positive pole. So the carbon dioxide molecule is a non-polar molecule, even though it has polar bonds. because even though a bond may be polar, overall those bonds kind of add up to be nonpolar. Another way we could visualize this is if we use our little vector arrows here. It almost looks like we're trying to have a tug of war, pulling from the middle, and neither of those oxygens is going to win because they're pulling equal and opposite directions. Does everybody see that? Or, I mean, we're going to do a few more examples. So if we feel comfortable with that, let's look at carbon monoxide. Okay, carbon monoxide just has one carbon-oxygen bond. And we know that a single carbon-oxygen bond is polar, so the carbon is partial plus, the oxygen is partial negative. Is there a place that I could draw a line in this molecule that would put all my positives on one side, all my negatives on another? Yes, I can put it right in the middle, right? Positives on the left side, negatives on the right-hand side. So carbon monoxide is a polar molecule. Okay. So two different compounds, both made with carbon and oxygen, based on, I hope you can see how the molecular geometry influences your outcome. Based on your molecular geometry, one of them is nonpolar and the other is polar. And you have to be able to draw it and see it in 3 dimensions in order to see that the molecule is polar. Okay, let me see if I can pull out a couple of other examples. Okay. Let's see here. Rather than copying and pasting these, we'll draw some of these. What if we had a molecule like CH4? So CH4 has 4 bonds to hydrogen, and I'll give you the Vesper shape on this one because in order to determine if this molecule is polar, the first thing we're going to ask is an individual bond polar? So is the carbon-hydrogen bond polar? I'm just putting a little set of instructions here. Okay, you guys are all telling me that the carbon-hydrogen bond is not polar. Okay, so I don't have any separation of charge here. What about this carbon-hydrogen bond? Is it polar? No. That was a trick question, Caleb. They're all the same, right? Each carbon-hydrogen bond is the same. So none of them are polar. So if we've then put all of the little partial positives and partial negatives on the molecule, I think you were being funny, Caleb. That's my, I'll defend you. There are no partial positives and partial negatives because none of these bonds are polar, right? Because carbon is 2.5 and hydrogen is 2.1. So there's a difference of 0.4. So this is on the nonpolar side. So, all right, now you guys tell me, is there any place I can put a line here and find positives on one side and negatives on the other? Nope, because there are no positives and no negatives in the whole thing, right? So one thing we find is that if we don't have any polar bonds, well, hello, nonpolar bonds, then I can't have a polar molecule. Because the whole point of being a polar molecule is that the charges from those bonds add up. Okay, so no polar bonds, not a polar molecule. Here I have polar bonds, but I'm a nonpolar molecule, and here I have polar bonds, and I have a polar molecule. So we've got a bunch of different options here. Let's do, Diana, well, you're exactly right. Here's an example of where we have bonds that are polar and we had a nonpolar molecule. But here, if we don't have any polar bonds, then we can't have a polar molecule. Okay, next, let's do NH3. So first I draw the Lewis dot structure, and from there I draw the Vesper shape, and then I'm just gonna skip a step here and give you guys the Vesper shape and have you guys tell me. Okay, look at bond polarity. Is the nitrogen-hydrogen bond polar? And why? Because the difference is 0.9. Nitrogen is 3.0, hydrogen is 2.1. Again, you just pick that up from the table of electronegativity values that you will be given on a test. Difference of 0.9, that puts it in the polar range. Okay, which side gets the partial positive, which side gets the partial negative between nitrogen and hydrogen? Caleb, if you're talking about the CH4 here, you are correct. It wouldn't matter whether I had just 2 hydrogens or 4. The fact of the matter is, if the difference is so small, if you have nonpolar bonds, you can't have a polar molecule. And Shauna Meredith and Jay Houston are exactly right. For this nitrogen-hydrogen bond, nitrogen gets a partial minus, hydrogen gets a partial plus. For this nitrogen-hydrogen bond, again, the nitrogen gets a partial minus, hydrogen gets a partial plus. For this nitrogen-hydrogen bond, nitrogen gets a partial minus, hydrogen gets a partial plus. Same story each time. Everybody agree with me? Excellent. Now the next question, step 4 here, evaluate molecular polarity. Does this pass the line test? Am I polar overall? Can I draw one line where all the positives are on one side, negatives on the other? Jay Houston says yes. We draw a line right here, positives on one side, negatives on the other. So this is a polar molecule with polar bonds. So I have polar bonds, and those do overall contribute to a polar molecule. Doesn't always happen that way, but in this case it does. And we can see it because we applied our polar bonds to the correct Vesper shape. Okay. Let's do another one. I hope you can see how drawing these in the Vesper shape helps you really visualize this pretty clearly. Let's do CF4. So if we do CF4, again, it's a tetrahedral shape. Can anybody tell me if the carbon-fluorine bond is polar? Yes, it is. We do have polar bonds. And you guys came up with that because carbon is 2.5 and fluorine is 4.0, right? Difference of 1.5, that's definitely within our range. Okay. So now let's just put these bond polarity here. So which side gets the plus and which side gets the minus? Fluorine gets the minus because it has a higher electronegativity. Excellent. So partial minus on the fluorine, partial positive on this carbon for this bond. And then we'll evaluate this bond and we'll say partial minus on this fluorine, partial positive on the carbon. And then we can evaluate this bond. Note we do each bond independently. We get a partial negative on this fluorine, and a partial positive on the carbon. And finally, we'll do this bond, partial negative on the fluorine, partial positive on the carbon. Is this a polar molecule? Sarah says no. Taylor says no. Caleb says no. Excellent. Non-polar molecule. Why not? You can't draw the line, okay? It does not pass the line test, okay? We don't have one side that's negative, one side that's positive. So I don't have two different poles, so I can't be polar. So here again is an example with polar bonds where I am a non-polar molecule. Let me do one more, and this one I want to start from scratch and give you this. Step one says draw the Lewis dot structure, right? So hydrogen comes in with 1 electron, and I've got 2 of those. And oxygen comes in with 6 electrons, so I have a total of 8. And then oxygen's in the middle, so it's attached to 2 hydrogens. I've used up 4 of my electrons. Next, I distribute the remaining 4 on the exterior, which don't want any, followed by the interior. So here we go. Now I'm out of electrons. I evaluate the structure. Is this the right structure for H2O? Or I should say, is everybody happy? Yes, yes, yes. Okay, so I did step one, which was the right Lewis dot structure. Now, could I skip a step and just go straight to polar bonds? Can we try that? Or should we draw the Vesper shape? Wouldn't it just be easier if I could just do it right here? Uh-oh, you guys are telling me I need to do the Vesper. Okay, all right, fine. Okay, how many electron sets are there surrounding that oxygen? 4. So those electron sets, those 4 sets of electrons are going to take on this tetrahedral shape. Okay, so I'm going to put the hydrogens here and here, and then I'll put my lone pairs here and here. And then my lone pairs don't actually are not part of a bond, so I can erase the bond. Okay, so there's my correct Vesper shape. All right, so now I could do the next step, which is bond polarity. Is the hydrogen-oxygen bond polar? I've got 1 yes. I've got 2 yeses. Okay, since oxygen is 3.5 and hydrogen is 2.1, the difference is 1.4, so that is in the range of polar. Which side gets the positive, which side gets the negative? The O gets the negative. Okay, so partial negative on the O, partial positive on the hydrogen for this bond. Then partial negative on the O, partial positive on hydrogen for that bond. So we already determined that this has polar bonds. Is this a polar molecule? Oh, 1 no, 1 yes. 2 yeses, 3 yeses. We can draw a line right here. And that puts all my positives on the right-hand side and all my negatives on the left-hand side. A little bit harder to see, but if you can draw a line anywhere, then you got it. Okay, so this is in fact a polar molecule. All right, but one thing to note before we move on, and this is why I went through the whole process here, is that if I stopped and did it here, if I stopped at my Lewis dot structure, negative, positive, negative, positive, and evaluated it here, this does not pass the line test. You would have incorrectly told me that this is a non-polar molecule because you're looking at the incorrect linear shape as opposed to the correct bent shape. Does everybody see that? Okay, this is why This step is so important. You can't do it from the Lewis dot structure because it doesn't tell me anything about shape. Lewis dot structure is great for telling me how those electrons are distributed, but it's not so good at telling me what the shape of that molecule is. And this is important for being able to determine molecular polarity. Okay, so don't take shortcuts, just do each step. You've got plenty of time, okay? Shauna Meredith wants me to do H2S. So we can do H2S. I have no problem with that. H2S looks like H2O, except it has a sulfur in the middle. So here we go. Here's my H2S. And if I'm looking at the difference in electronegativities alone, since sulfur is 2.5 and hydrogen is 2.1, then I would say nonpolar bonds, and therefore nonpolar molecule. For the purposes of this class, that's what you need to know. This is, now having said that, I will tell you that there is a bit of an exception whenever we stick hydrogen, which is this teeny atom up here, with anything that's in the third row or below. So like with sulfur or phosphorus or even bromine, selenium, the fact that you have something that's so tiny paired with something that's so big, you just can't share very well. You don't have very good atomic overlap. And then because, say, the sulfur is so big and fat, it just naturally ends up being a hog, not because it's a bully, but because it's big. So the true answer is that it's polar, but it's polar by size. I will never test you on that level of exception, okay? At this point, I just want you to be able to identify it if it's polar by electronegativity. And hopefully that will answer any question that might come up from the homework. So let's see, let's look at, some of these might be on your in-class activity sheet. Yeah, let's look at the in-class activity sheet. We can do a few more examples. I'm assuming you guys want more examples, or do you guys feel so awesome great at this? More examples, excellent. I've got 2 people voting for more examples, Robin and Jeannie Lind. Anybody else? Shauna's like, yeah, this is also good, awesome. We'll just do a few more and then we can move on. In section 3, I was really nice and I gave you the Vesper shape. So you just have to tell me polarity or non-polarity. And then section 4 is excellent exam practice because it takes you all the way from the beginning. I give you the formula and you've got to, 1, determine your Lewis dot structure so that you can step 2, determine the Vesper shape, so that then you can step 3, evaluate your bond polarity to determine your overall step 4 molecular polarity. So you can see, as is usual for the in-class activity sheets, I try to take you from one step to the next step to the next step. So we can do a few of these in section 3 and then we can do a few in section 4. Shauna Meredith, not Shauna, sorry, Robin particularly asked if we could do HOCl. So let's do HOCl. I've given you this shape here, which is bent, and now we have to say, is the OH bond polar? Is the OCl bond polar? What can we find from there? So for the OH bond, you guys tell me, is it polar? Shauna says, oh yeah, it's polar. Hydrogen's 2.1, oxygen's 3.5. That's a difference of 1.4. Definitely polar. And pulling towards what? Towards the O. Okay. So partial positive on my hydrogen, partial negative on my oxygen. Okay. What's the electronegativity value for chlorine? 3.0. So the difference between when we're evaluating just the OCl bond, we've got a difference of 0.5. Is that polar or nonpolar? It's kind of on the line, right? On the line that I gave you. We can say that it's polar, ever so slightly polar, barely polar. If it makes us feel better, we can give it just like a teeny plus and a teeny minus. Does that make us feel better? Because it's definitely not as polar as this OH bond. But we could say it's a teeny bit polar. Okay. All right. Next step, line test. Is there a line, place where we can draw a line? Puts the positives on one side, negatives on the other? There sure is. Right down the middle. Positives on the right, negatives on the left. So then this is a polar molecule. I'm glad that you pulled up this example, Robin, because it's interesting to see when we've got more than just two different types of atoms here. Note that we never at any time compared hydrogen versus chlorine. We didn't do that because the hydrogen was not stuck to the chlorine. There was no bond between the hydrogen and chlorine, so we never compared how well they're going to share electrons because it didn't matter. They weren't sharing electrons in this particular molecule. We only ever look at the actual bonds that we have in the real molecule. Excellent, excellent, excellent. Okay, let's do part 4. And this is going to take a little extra time because we're going to have to draw Lewis dot structure first, and then Vesper shape second, and then evaluate. I don't want to do all of them. Actually, we could. We've got the time, but it sounds like half of you guys are feeling excellent about this. So let's just pick out a few that we feel good, that we want to see. You guys give me a couple examples you'd like to see, and we'll do them. Okay, we'll do this one. Other votes? Excellent. This one. Other votes? Excellent. This one. Any other votes? One more. Okay, that's what I thought. You guys pulled out all of the ones that had more than 2 different types of atoms and one that has 2 different central atoms. Good. Those are excellent. Diana, do you have any other votes? Last vote. Okay, same thing. All right. Well, let's start with CH2O. And remember, and I think I might have told you guys this in class, as you're doing the in-class activity sheets, I do recommend that in margins you say what you're doing so that as you go back to study, you can not just see what the answer was, but you can see how you got there. So step 1, we're going to draw the Lewis dot structure. In step 2, we're going to draw the Vesper shape. In step 3, we're going to look at bond polarity. And then step 4, we're going to do that line test to look at molecular polarity. Okay. And you might find that you need a little bit more space than I've given here for all of those things. So if you want to do, for instance, the Lewis dot structure on a different sheet of paper and then draw your Vesper shape here, that's fine. Because I'm going to take up more space than just this little piece here. I'll draw this Lewis dot structure over here. Carbon comes into the game with 4 electrons. I have 2 hydrogen atoms. They each have 1 electron. And I have 1 oxygen atom, which comes into the game with 6 electrons. Remember, these are the valence electrons. And that gives me a total of 12. So carbon's listed first. It's in the middle. It's attached to 2 H's and 1 O. And here I've used now 6 of my 12 electrons. Next step says I need to distribute remaining electrons on exterior atoms first. This oxygen has 2, it wants 8, so I'm going to put all 6 of my remaining electrons on the oxygen. And then I'm out of electrons, so the last step says evaluate, is this the right structure? No. What do I need? What's wrong? Carbon needs an extra bond. It only has 6 electrons. So I'm going to take those last 2 electrons I put on the oxygen, and I'm going to move them there. Is that good? Everybody happy now? Excellent. So I've done step 1. Step 2 says I want to draw this in its correct Vesper shape. So valence shell electron pair repulsion theory says, how many electron sets do I have around that central carbon atom? One vote for 3 and 2 votes for 4. 3 votes for 3. Okay. Many more votes for 3. Yes, there are 3. Yes, because the double bond counts as 1. So it's true that there are 4 sets of 2 electrons, what we call an electron set for the purposes of Vesper shape. A double bond counts as just 1 set. So I have 3 sets of electrons. That's going to make my shape what? Trigonoplanar. So carbon in the middle. So oxygen at the top of this triangle, hydrogen bottom right, hydrogen bottom left. So here now, step 2, I've drawn this molecule in the trigonoplanar Vesper shape. Excellent. Next step, bond polarity. Is the carbon-hydrogen bond polar? Nope. Carbon's 2.5, hydrogen's 2.1, difference of 0.4. That's going to be on the nonpolar side of what we call bond polarity. So nothing there. Carbon-oxygen bond polar? Yes, carbon is 2.5, oxygen is 3.5, difference of 1. So I get partial positive on the carbon, partial negative on the oxygen. And this carbon-hydrogen bond, the same as that carbon-hydrogen bond. Now, is the molecule polar? We've put in all of our little partial negatives and partial positives. Can I draw a line and put all the positives on one side, all the negatives on another? You guys are right. The hydrogens don't have a little partial anything, so they're just not considered for the purposes of this argument. We're only interested in where we do have partial positives and partial negatives. That's where we draw the line. And we can say, yep, that's a polar molecule. Done. Now that was a lot of steps to come up with that answer, wasn't it? Yeah, there's a lot of steps, but you guys can do it. You can do it. I know you can. So on the exam, I might have, say, like a list of 5 molecules and say, which of the following molecules is polar? And there will only be one answer. There's only ever just one answer. So which one of the following molecules is polar? Okay, let's move on. Would you guys like to learn one little trick that might save you a teeny bit of time? Yes, of course you would. Okay, remember here, if I have polar bonds, I might be polar, I might be nonpolar. But if I have nonpolar bonds, I'm only ever nonpolar. You guys remember that? Because if I have polar bonds, these may add up, they might not. If I don't have polar bonds, I don't have anything to work with. So knowing that, if we look at something like, if we do this step first, to say, is it even possible for me to have polarity? Like, do I have polar bonds to work with? That can help save me some time. So for C2H4, I could have bonds between carbon and carbon, and I could have bonds between carbon and hydrogen. Those are all my possibilities. Are either of these bonds going to be polar? Nope, nope, nope. Carbon is 2.5. If it's bound with itself, it's obviously not going to be polar. Hydrogen's 2.1. That difference is not great enough. I have no polar bonds in this molecule. Polar bonds. Therefore, I don't even have to draw it because I know I won't be a polar molecule. And that saved me a little bit of time. Can't do that all the time, but you can sometimes get away with that. Is that a nice little trick? Saved us on one of these four. So, 25% of the time might be helpful. Okay, let's look at HCN. If we have hydrogen, carbon, and nitrogen, if hydrogen is 2.1, carbon is 2.5, and nitrogen is 3.0, is it possible that we could have polar bonds in this molecule? We could, depending on what's bond done to what and how that works out. So now that we know that we could have bond polarity, we better go through all the steps. Yeah, the C and the N could be slightly polar. If H is bound to N, then maybe. Okay, let's go through the steps. Number one, draw the Lewis dot structure. Hydrogen has 1 electron, carbon has 4, nitrogen has 5, so I have 10. So carbon's in the middle, hydrogen, nitrogen, I've used 4, I've got 6 left. Exterior atom, 2, 4, 6. Now I'm out of electrons. Is everybody happy? Anything else I need to do? C is mad. He's so mad. What can we do to make C happy? Okay, let's way ahead here. Not just sharing 1 extra pair of electrons, but 2 pairs of electrons. That's what we're going to need. Excellent. Okay, now we've got the right Lewis dot structure. Vesper shape. What is the geometry going to be surrounding that carbon? Linear. Excellent. Carbon in the middle. Linear. I don't really need to redraw it, but I want it to make it really nice and neat and clean. Okay, now evaluate each bond. Is the carbon-hydrogen bond polar? Nope. Small difference. Is the carbon-nitrogen bond polar? Yep, ever so slightly. So, positive. Notice how I'm making these like really teeny. Teeny positive, teeny negative, because it's barely. So was this molecule then polar? Does it pass the line test? Sure does. It's a very slightly polar molecule. Of course, for the purposes of our class, we're not going to be testing on slightly and highly. We're just going to say it's polar. Everybody follow me there? Any questions before we move on? No questions. Okay. Thank you for responding. At least letting me know there's no question. Even if you have no question, it helps if you say that, and so I know. All right, first CH2F2, carbon, hydrogen, fluorine. Carbon is 2.5, hydrogen is 2.1, fluorine is 4.0. Is it possible that this molecule could have polar bonds? Yes. Okay. Fluorine and hydrogen are definitely big enough difference. Carbon and fluorine definitely big enough difference. Okay, so Lewis dot structure, carbon comes in with 4. I've got 2 hydrogen atoms that each come in with 1, and I've got 2 fluorine atoms which each come in with 7. I think that adds up to 20. Did I get that right? Okay. Carbon in the middle, 2 hydrogens, 2 fluorines. I've used up 8 of my 20 electrons. I have 12 left. Next, distribute remaining electrons around exterior atoms. Each of my fluorine atoms has 2 1/8, so they each need 6 more. 2, 4, 6. 2, 4, 6. So now I've used up 12 and I'm all out of electrons. Is that molecule happy? Is that the right Lewis dot structure for this molecule? Yes, okay. Now draw the Vesper shape. What's the shape of this thing gonna be? Tetrahedral. Excellent. Okay, so carbon in the middle. We're gonna have kind of bent in the plane, 2 outside of the plane. And here's one case where it doesn't matter where I put the hydrogen atoms and where I put the fluorine atoms. Because wherever I put them, I'm just looking at the same molecule from a different perspective. But for the purposes of seeing whether it's polar or not, it will actually help us if we put the same types of atoms on the same side. So I'm going to put both hydrogens on the same side or both fluorine atoms on the same side. That's going to help me see it. But it really doesn't matter. It's just being able to see it from perspective. Okay. All right. Carbon-hydrogen bond. Is that bond polar? Nope, nope, nope. Carbon-fluorine bond. Is that bond polar? Yes. Partial positive, partial negative. Carbon-fluorine bond. Is that bond polar? Yes, thank you. Partial positive, partial negative. Okay, next, we've looked at all 4 bonds. Step 4 is my line test. Is there a place I can draw this line? Yes. This is a polar molecule because I've got the positives on the left and the negatives on the right. All right, that is it for molecular polarity. I'm going to stop this recording. We'll take about a 5-minute break and then we'll come back and talk about nomenclature.